Greetings, everyone. I apologize for having to record this separately outside of class time, but since the semester is winding up here in a couple of weeks, we have other material that we really have to move on to here in the end. But I want to make sure that these examples are available so that you can refer to them while you're attempting your final lab in class. And so hopefully these recordings will help you during that last Thursday lab day that we have coming up next week. You can watch these videos and hopefully it will help guide you to the correct solution. Okay, so we have actually 4 examples to go through. These examples are on Canvas. So let's start with 1 here. This is 1.c in that archive. If we go to the main function, where we always begin, we can see that it does 2 things. First, it calls mess with heap. Mess with heap is here. And that will prompt us to enter a size. Scanf will collect that size. Then there's an evaluation. If size equals 0, then we break. So that's how we end the program. We enter 0. Anything else we enter will malloc with the size we provide to the variable p, memset x's, however many we enter, into p, and then free it. And this is while 1, so essentially forever, or until we press 0 to break, right? After we return from that, main calls allocate specific things, which is directly above. There are 2 variables. One 16 bytes, the other one 32 bytes, where A, which is 16 bytes, gets the string important info copied into that location, and the 32 byte version, there's a gets for B. We can run this. There we go, 1 bin, 2 bin, and a make file. We don't have any Python scripts for these at all. We don't really need them, right? So if we run 1.bin, there we go. That's what we expect to see. Enter size, which means I know that it just malloced 32 bytes and then freed it right away. We can do that as many times as we would like. And each time it's creating, allocating, and moving on. Now, I'm not covering, again, the debugging methods that we covered on Tuesday. That recording, or those steps, I should say, are in the lecture recorded for that day. So instead of going through all of that again, I'm going to just simply start our debugger here so we can actually see what's going on, hopefully. So break main, and then let's run it, and I'm going to set another breakpoint, and I'll set it, how about we set 1 right here before we call allocate specific things. And how about we set another 1 directly after allocate specific things, so that we can, at 2 different points, see the state of our chunks. Okay. All right. So let's continue on then, and let's do. Let's see. Let's do. We'll do 132 byte. Right. So that is p equals 32 x's. Let's do how about a 48 bytes? How about we do another 48 bytes? How about we do a 128 bytes? How about we do 120? How about we do a 16? How about we do another 16? How about we do another 32? And let's break. Okay, so we enter 0. We are now out of the mess with heap function. We're back at main plus 18 to the second breakpoint we set, which is that clear EAX call here before we actually call to allocate specific things. All right, so we're zeroed. Good to go here. And let's take this as an opportunity to see what the chunks look like. So we carved a bunch of chunks off that top chunk here's our top chunk here. All right, we can see how many bytes are left. Here is hex 20, so that is 16. Here we have our hex 30s, that's going to be our 32. 40 is going to be our 48, and notice that the hex values are slightly larger than what we actually allocated because of our overhead with the metadata and so on, but also making sure that we're aligned on 16 bytes. So, you know, for example, this hex 90 here, which if we take a look at the calculator, hex 90, that's 144 bytes, which, you know, we had requested 128 and 120, so significantly more than we had requested, and so on. So that's the state of our chunks. How about bins? Okay, we can see that the tcache bins here, we have several sizes. Our hex 20, hex 30, hex 40, hex 80, and hex 90 have at least one chunk in them. Each of them, in fact, have one chunk in them. And if you recall, the reason that we have but one chunk, like for example, we have only one here in hex 40, but we called 32 bytes at least twice, right? Yeah, one here and one here. Our 16, so our hex 20, there was two chunks called, but there's only one entry in our bins for that. And that's because they were recalled, right? They're freed in the code just as soon as they are returned to us. We're just reusing that chunk. It's just going back and forth, right? Let's examine the memory space here. Let's see, our top chunk address is this. So let's examine. We'll do 400 giant words in hex at that location. And here's our hex 5858. If you're not sure, we can check an ASCII table. That should be a capital X. Hex 58. Indeed, that is a capital X. So here are the X's that were put into those variables as we moved about. Here. Here. So that's the tour of more or less where we are. Let's see. Let's go back to context. All right, so we haven't yet allocated specific things, so let's do that. I probably should have set another breakpoint for directly after this, huh? Oh, I did. Okay, so we do have another breakpoint. Okay, now let's check the status of our bins. And that, what that did is that malloced a 16-byte value and a 32-byte value, which we had called each of those twice, but there was only one chunk that was freed. So now our hex 20 and hex 30 tcache bins, they're gone because those chunks have been recalled. So now if we go heap chunks, here, hex 20, and now that says that string that was copied in there, important info. Here's hex 30, and in between there we've got 40 and 90. There's a bunch of chunks here that were called before. So now what this sets us up to do, if you recall the slides, is something known as heap grooming, right? So what we basically can do with this program is we can intentionally manipulate the heap chunks, right? If we call certain values in a certain order, we can essentially ensure that our 32-byte value and 16-byte value remain relatively close to each other, in memory. Right now they're separated by three chunks, separated by three chunks, because when we requested these sizes, we requested a 32, and then we requested a bunch of other sizes until eventually we got to 16. It was fairly low on our list of values to call. Hopefully it's not too far up. It might be buried. But let's see if we can still see that list. Yeah, there we go. So we didn't call a 16-byte value until, I mean, we called the 32 right away, but we didn't call a 16-byte value until after we called a couple of 48s, which this would be one entry, because we called a 48, freed it, and then called a 48 and freed it, so it's going to use the same chunk. Then a 128, and then a 120, and then we finally got to 16. So that's why there's three chunks in between them, because we called three different chunk sizes. 32. The 144 is going to be the 128. The hex 80, that's going to be the 120, which, if we check that value, hex 80, that is 128 total. Hex 90 is 144. So the 128 actually reserves 144 bytes. The 120 actually reserves 128, and so on. So we have those three chunks in there because that's the distance between our first request and the three unique values after that before we get to 16, right? What was I saying? Oh, right. So we're going to be working towards here is a heap overflow, and that's coming from this allocate specific things function, because this is doing two things. Here's our sensitive information, or our analog for sensitive information in this case, and if we can pop this higher up, right, in this list of chunks, than our allocation for 32, then when we get to this gets, if we exceed the bounds that have been allocated for B, then we are, let's do the thing again here. There we go. 81, 91, 41, 31. There we go. So we've got three values between us now, but imagine that we have this chunk and this chunk right next to each other. If we write to this chunk and overflow it, then what do we begin writing to? The other areas of adjacent memory, which means that we can overwrite, right, here's the X's that are going here, into the metadata and essentially adjust the size that's being recognized for that value, or, if we continue going beyond that, then the data that's literally held in that area of memory. So let me show you what this looks like before before we actually make use of this for any kind of a practical exploit. We'll just do a regular overflow. Okay, so we'll run it again. All right, we are going to mess with the heap and run that. We're going to allocate a 32-byte value and a 16-byte value, and then we're going to quit. All right, now we're going to let the allocate specific things run, and there's our gets statement. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and we'll overflow here. How about 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we should, there's no bounds checking here for this this get statement. That's the problem with this statement. And so if we throw that into there, all right, we're at our next breakpoint. And now let's see, first of all, what our chunks look like. Not break chunks, heap chunks. All right. So we can see, excuse me. Here's our size 30 chunk. That's our 32 byte chunk. Look at our size of our chunk that was previously hex 20. It's now 464646. And again, if we get our ASCII table up here, hex 46 is capital F. So when we overwrote that, we have our 41 here. That's our A's, B, and all the way to F. We can probably see it better if we examine this. So let's examine. Yeah, here we go. So here's the 8 A's we entered, the 8 B's we entered, the 8 C's, the 8 D's, the 8 E's, and the 8 F's. This was the metadata for that hex 20 chunk. And the important info is still there in the memory address directly after this. So with that overflow, we've essentially been able to successfully modify the adjacent chunks metadata, in this case with arbitrary values, but if we were to massage those values and place something specifically in that place, well, we might be able to do something here. So now in this case, overwriting the metadata might be useful to us, down the road here. But if we run this again, and let's say that this important info here, let's say that that is a stored PIN or password, like with the example in Lab 5.2. If we continue this, let's run it again one more time. And we're at our first breakpoint. This is right before mess with the heap, so let's move into that. And again, we'll allocate a 32-byte and 16-byte chunk and quit. And then we will again go through here and let it gather our data. And this time, we will enter, how about ABC 123 00000. Okay, now let's see. Actually, we'll just go right to the examine, I think. So now, here, as we saw before, our A's, our B's, our C's, our D's, our F's. Oh, I was a little bit off. I miscounted. But still, here would be our A. I would need to add one more character here because I miscounted the number of A, B, C, D's, it looks like. But A, we know, is 41, B, C, and then we have 1, 2, 3, right? So I can, and then the hex 3 O's for the character is 0. So I've overwritten the important info here. Actually, I suppose I missed part of it, but in any event, you can see the practicality here. Whatever that PIN or password was has been replaced with my own value, right? All right, let's check out example 2. This one's going to be a slightly different example. With this, we can do something called tcache poisoning. There's a slide for that up in the lecture deck that explains the process, and we'll step through it here with number 2. But what we have here is a simple program. Here's our main function. We malloc 2 variables, 16 bytes. We free them both up. After they're freed, we try to use them. In this case, we're using B. That is a use after free vulnerability, which means that we have at first, so our tcache bin is null. After we free A and then free B, it goes null and then A and then B. last in, first out. This one's in the middle. This one is the null pointer. We try to use B. It's referenced. We know where that is. But use after free allows us to overwrite the next pointer in B, so that instead of pointing to A, it points somewhere else. Our target hello world here, perhaps, for example. We allocate B again, so that our pointer, the one we just added here to our mystery location, will be the next in the free list, because again, first in, last out. If we malloc B again, or another 16-byte chunk, it goes to the 16-byte tcache and says, oh yeah, I just used one of those, kicks that back out to us. But instead of pointing to A now, it's pointing to the next value, which is whatever we have overwritten. Which means that when A is malloced, it goes to the tcache bin and says, oh yes, I have an entry here for something that says it's a 16-byte value, but it returns the pointer that we added instead, and calls that. String copy. This is fine. Print target. So we're going to say so the beginning of target is hello world, and we're essentially changing that to this is fine. Okay? Let's quit GDB. Let's run that run that program here, and we'll debug it so you can see how all of that is working in the other side. Break main. Oops. Okay, and again, this was compiled with the G switch, so you can see what's going on here in the source code. So we're going to, next, this is our malloc for A, malloc for B. We can check that. There we go. We have two size hex 20 chunks. Now we're freeing A. Now we're freeing B. All right, so our two hex 20 chunks, they've been freed. There's a pointer off to them. So now if we check our bins, here we go. Just as we saw before, there's going to be null at the end of this. Our first chunk and second chunk. Chunk A. 52AO. Okay, yeah. That was the right order. Null A B. Okay, but now we're at this gets statement. Context here. So we're at the get statement. This is our use after free error. B has been freed, but we're calling it for a gets anyway. And that is something of a little bit of an issue for us. But for now, let's just play this out, and we'll do the gets, and I'll just enter just 4 A's, just to give us some data that we can kind of keep track of. Okay, that's done. Let's see what happened here to our chunks, even though they've been freed. Well, what we see here is that since B was freed, this is B right here. We know that AO is A, CO must be B. That the value did go somewhere. It had to go somewhere, right? But there we go. The chunk for B is still there. But look what happened to the chunk for A. Corrupted chunk at 4141, etc., etc. That's not good, right? That data overwrote that tcache information. So, as we just saw in the code here, what happens when we then later on need to get back that second hex 20 chunk? Well, let's find out. Wrong window. So where we are right now, we're going to malloc B again. Look at our RSI for malloc here. There we go. B has been malloced again. It's the state of the bins now. B is gone out of the tcache bin. The next thing on deck is that corrupted chunk that we managed to overwrite. Heap chunks. Here we go. B is still there, where it was before. A is right there. Okay, so now if we malloc A again, and we will copy, this is fine. Since we're mallocing another hex 20 value, and there is an entry in the hex 20 tcache bin, this is going to try and call back that next entry, which of course is corrupted, as we just saw. Stopped. That command, there we go. We got a SIG abort. So that corrupted chunk, it was pointing to a memory address that wasn't valid, so wasn't useful. But what if it was? What if we did put a valid value there? Okay, so that's it then for these first two examples, and let's move on to the next pair. So let's jump right into it. Here we have 1C. So this program here declares a couple of variables. It allocates 9 things of the same size, so 9 16-byte items here in a for loop. 7 of them being, whatever this loop is, and then A and B for a total of 9. Then we free the first 7, so the first 7 things that we allocate. And 7 is the magic number because if you remember from the lecture slides, the tcache can hold up to 7 items, and then after that we start getting into our fast bins and so on. And that's exactly what we're going to do. Right? So that first 7 items is going to fill our tcache bin after we free them. And A and B, when they get freed directly after, they can't fit in the tcache. The tcache is full, so they're going to go into the fast bins. So our bin state at this point will look a little something like this here, where our tcache will have the first 7 items, 0 through 6, and then A and B will be in our fast bins. So we've already just freed A, but we're going to add in an accidental double free. So it's a double entry in the fast bin, meaning that our link list in the fast bin is now going to go A to B to A, and that's going to be a problem. Because if we recall A, B is next on deck, and then what if we call A again? We reallocate those 7 things and empty out our tcache. We reallocate A, so this first A, that goes back to being reallocated for A. We reallocate B, well, that's called next, that'll be reallocated for B. But when we call C, it's going to look in the fast bins, it's going to say, oh, sure, certainly I have an entry here of that size, but the address it's pointing to is A's current address because it was listed twice. So we're basically going to have 2 variables pointing to the same address. So what we're going to do is we're going to put A's in A, we're going to try and put C's in C, and then we print out the contents of A to see what's in it. Okay, so let's run this one. 1.bin. So the contents of A is C instead of A. And the reason for that is because A and C are pointing to the same memory address. So whatever we do to one is happening to the other. Variable names are not necessarily distinct. They just represent like a alias, if you will, for a memory address. And of course, you can have multiple names. You can have multiple aliases. And what we've done in this case is accidentally created a scenario where we have 2 variables pointing to the same address. Now, this can be useful in an exploitation sense because if A contains sensitive or secret information, and we can manipulate the program as such that we can fill up the tcache and create this exact scenario for ourselves. And let's say that C is a variable that we have ready access to. C will be possibly, well, as you'll see in Lab 6, maybe it's a note, or maybe it's a name, or something like that. And then that means that if we get into this situation where A and C are pointing to the same address, then when we call C, like to read a note or to display the username, then it will instead point to the same data that's at A, which will be our secret. So keep that in mind for Lab 6. Oh, you know what? Maybe I should, maybe we should debug number 1 before we move on. So we can see what that looks like with A and C pointing at the same variable. Okay. Here we're allocating all 7 onto the tcache. 5, 7 there. Okay, now we're gonna, well, let's heap bins, and those will be empty because we haven't freed anything yet. But if we heap chunks, there's the 7 items that we just allocated. We just allocated A and B. Now we're gonna free the first 7, but first, I suppose, there we go. A and B are now included in that. They're all the same size, so we can't really tell, but we're there. All right, let's free up those 7. 4, 5, 6, 7. There we go. Tcache is full. We can see the count equals 7. Free A and free B. And because the tcache is full, we have 2 entries now in our fast bin, 1 for A and 1 for B. Okay, now we're going to free A. This is our double free. Okay, now let's look and see what we're at. Now the fast bins has 3 entries, but the address that's being pointed to for our first entry and our last entry is 9380, the same address for both of those entries. That is the issue that we're going to have here, because now we're going to empty out the tcache. I'm going to reallocate all 7 of these items, 5, 6, 7. All right. Now, tcache is empty, but we still have the 3 chunks in the fast bins. So let's allocate, reallocate A. Oh, you can see right here, loop detected. So we grabbed A, and now look, we've got 93A0, 93A0. So we pulled that first one out, but these now link to each other, right? Because B linked to A, but then when we double freed, A linked to B, linked to A, linked to B, linked to A. That's where that loop is coming in. If we now allocate, oops, B, we still have an issue with the loop. Right? All right, now let's allocate C. Actually, let's look at the status of the chunks here. All right, there's all of our chunks. Okay, copy all of those A's into A. Hex 61 is lowercase a, so that's where those ended up. So that's A right there. Now let's put those C's in C. And there we go. Because they were both pointing to 9380, all the lowercase a's were overwritten with lowercase c's. So that now when we print out those values, we get the c's back, but we instead, it looks like Jeff crashed. Hold on a sec. Oh, no, there it is. So it did print it out. Did we get a crash from... no. Single step, and then it was done. Okay. I expected to see something from Jeff, but that's fine. So that's how that one works. So sorry for hopping back and forth here, but now getting back to 2. Our second example here, we have another fairly simple program. We have some variables that are declared. 24 bytes are allocated for A, B, and C. We copy into C our secret information, very important info in this case. And we're going to do a 1-byte heap overflow. So we have a off by 1 error here. We have A, which is 24 bytes. We can see that we've allocated 24 bytes for it up here. But down here, this for loop is running starting at 0 to when I is, while I is less than or equal to 24. So how many times is this loop going to run? 0 through 24, 25. So we're going to be off by 1 on our A variable. All right, so we have an off by 1 error here. So A is going to be overflowable by 1 byte. So the heap chunks are going to look something like this, which I will remember to debug it right away, so we'll be able to see it. Then we free B. So A is in use. Now B, which wasn't used previously, is being freed right away. But we had an off by 1 error here, which means that the metadata for A is going to be hex 20. It's going to have up to hex 20 A's, but because we're off by 1, that extra byte is going to go ahead and overflow and overwrite the metadata for B. But B is freed, right? Which means it will get added into the tcache bin for that size chunk. But since the metadata has changed, then it's going to end up in the wrong bin, the wrong tcache chunk size bin, right? Looking something like this, right? So A is still up. We got that overflow on that. B is freed. It's in the tcache bin, but it's going to be in the wrong size tcache bin. C is still in use in very important info. Now, if we malloc B for 56 bytes, which is much larger than its original allocation, this is what we end up looking like. Right? The issue is that B now overlaps C. It's now twice as large, but it was thought to be the same value, right? So hex 20, but now it's hex 40. So it's doubled in value from that first allocation. And now, because B and C were allocated relatively contiguously, I mean, they were adjacent chunks is what I mean. B, the size of B, now technically extends all of the previous amount of B plus twice as much, which is essentially all of C's space as well. Right, so we run that 56 times, and that gets us what we need. We print the contents of C, and that allows us to access that space. Right, so let's run that. What? What is going on here? Well, let's just debug it. I don't know what's going on. Okay. It would be so nice to be able to do demos without something going wrong. Malloc A, Malloc B, Malloc C. Very important info goes into C. State of the heap right now. Heap chunks. Okay, C there is the last chunk we carved from the top chunk, so it's the one there on the bottom. You can see very important info. Okay, that's fine. That's what we expect. We off by 1 on A, so this is going to loop through a couple of times. $16. Okay, there we go. All right, except now the metadata has been altered so that B, so the 414141 here, that has filled up all of A, overwriting the metadata for B, which now thinks, because capital A is hex 41, it thinks now B is hex 40 in size. See, there's the metadata for chunk B. Here's our very important info. Here is the start, the metadata for chunk C. But B has been overwritten with a capital A, so the size is wrong. Now what we're going to do is free B. Heap bins. There we go. So now B is sitting here in the tcache for hex 40. Now what we're going to do is reallocate B for 56 bytes. There we go. The tcache is now empty. We still have the 2 chunks, A and B. B was brought back in as a hex 40 because that's the tcache bin it was in. Okay, and now we write B's to B, but only to the 56 times. There we go. Now we're about to do that print. All right, so those are all filled with B's. We've overwritten, here's where B begins. We've overwritten the metadata for C and all of the other data for C, effectively overwriting whatever security information may have been there. And then if we print it out, why is this print statement not working? Oh, because it can't find C anymore. No, well, point still stands. You could overwrite that security information. Also, if we had called B at any point after that overflow, let's do this here. So after this overflow, let's print the contents of B. That should show us the secret anyway. The contents of B is well, oh, now the print statement's working. What the heck is going on? Oh, the first print statement didn't work because B is empty. It calls B, and then there's null bytes because we don't fill it with anything. So let's put this here. And we want to run this. Well, it was 20, or no, was it 24? It was 24. So let's do this 32 times. And that should fill B up and print out C as well. Yep. Well, there we go. So we can do this two ways. We can do this to leak critical information, or we can overwrite critical information. I don't know why that wasn't working the last time, for some reason, the print statement, but whatever, we got it to work here. So in the first case, we essentially overwrite with just an off by one error the metadata, the size of chunk B. That causes the program to think that B is in fact hex 40 bytes instead of hex 20 as it was originally allocated. If we fill up B up to, once it's reallocated, essentially B owns the memory space of itself and C, which means that if we fill up the area that was originally allocated for B, that gets us to the very beginning of the data that was saved in C, and it effectively allows us to read from B to the end, which includes C. It also allows us to overwrite into C's memory space and change whatever happens to be there. So the first line that you see here, contents of B is, those B's are 32 B's that make up all that was originally allocated for B, which is the 24 bytes originally, plus 8 bytes for the first memory address of the metadata of C. And that gets us to the very beginning of the data in C. Very important info. Then C, that second, the contents of C that's a direct reference to the memory that was the pointer that's allocated for C, which just contains the information that's in C after we overwrite it, right? As a matter of fact, let's display this again, okay? And the second time we overwrite B, let's use lowercase b's so you can see a difference. See, there you go. Right. So the second time when C prints out, it's printing out lowercase b's because when we do that, we've actually overwritten the data in C. So if C was a password using this with this particular vulnerable application, we could either leak it or we could change it. Okay, these are some rough demonstrations, but we got through it, and I hope that all makes sense. Good luck on Lab 6. Do reach out early and often if you're having problems. But after this, you have only the final project to do, and you'll be all set. Okay. Take care. Have yourselves a nice week, and we're getting down to the end of it, so head down, power through. Okay?